Alright, so we're basically doing some hard integration questions today because later on we'll be using it for solving heat equations, and also we can use it to talk about Fourier transform, stuff like that. Now, by Gaussian integral, we're talking about the integral of e to the negative x squared dx. Which, if you are a hardworking student in Calculus 2, you would know that this is like one of the examples where you cannot find the antiderivative. Okay? The antiderivative cannot be expressed as basic functions. Right? Now there's a preferred type of Gaussian integral for physicists. This is the one that physicists prefer, but for some reason, statisticians like the one with divided by 2 over here. Okay. So what is e to the negative x squared? Well, e to the negative x squared, when x is a very big number, you have e to the negative infinity. That's like 1 over e to the infinity, which is 0, right? So this is a function which, if you plug in 0, you get 1. And if you plug in some bigger values as you go right, it goes down to 0 very quickly, and this is what's known as the bell curve. And the one that has, you can normalize this some way so that the area under the integral is 1. That makes this integration, this function itself, a probability distribution function. A probability distribution function is a positive function where the area under that is equal to 1. Right? And that's an example of a normal distribution. Okay? Now, the one with the over 2, that gives you the standard normal distribution with some coefficient in front. That's why statisticians like the one version with divided by 2. Okay? All right. So one thing that a lot of people would like to know is the value of the integral from negative infinity to infinity, so that if you know this value, then you can divide it by that value so that the area is 1. And if the area is 1, then you do have a genuine probability distribution function. Okay? All right, so how do you calculate this? The picture is what I just drew. It's the area below the graph of e to the negative x squared. There are basically 2 ways to go about solving this. One is to use complex analysis. There's some Resi calculations you can do to get the value of this, which is we didn't learn that yet, so we can't do it here. But the other method would be using the multivariable calculus by first saying that this is a square root of, you integrate, well, first of all, you can write this twice. We put one integral from negative infinity to infinity of this thing, but then you write this again, except this time you write as an integral of y. Well, it doesn't matter whether it's y or x, they would give you the same value, right? So indeed, this thing inside the square root is same as this squared, so they are the same. You agree? Right. But then this can be thought as a 2-dimensional integral, or it's a double integral, where because you have the same base, if you multiply these two together, it will be e of negative x squared minus y squared dx dy. Now comes something that you learned in multivariable calculus, that there's something called a polar coordinate system where r is equals the square root of x squared plus y squared, and theta is the arctan of y over x, and then you might have something additional depending on which quadrant this is in. And with this new polar coordinate system, dx dy also transforms as, does anyone know? It's something dr d theta. What goes here?
R.
R. Good, good. All right. So you can rewrite this. Oh, but before that, let's try to imagine what this integration is like. So if I say z is equal to e to the negative x squared minus y squared, well, that's like e to the negative x squared plus y squared. So again, so let's say z coordinate is coming towards you, right? When you plug in 0, at 0, 0, the height is 1. But then as soon as you increase x or y, you go this way or in any direction, it goes down to 0 quite quickly, right? So you have something like a bump that goes down to 0 quickly, okay? And you're trying to take the volume under the surface. See, in 2D, if you have a double integral of a surface, the double integral has the meaning of the volume under the surface, right? So we're trying to find the volume under this surface. That's what we're trying to do, okay? And you can rewrite that domain because we're letting x go from negative infinity to infinity and y to be negative infinity to infinity. This integration covers the entire R2, okay? But then because we're now changing that to r dr d theta, we can now let r go from 0 to infinity, right? And this theta to go from 0 to 2 pi. How's that? If you do that, then it also covers the entire two-dimensional plane, right? So what we have is the square root of 0 to infinity for r. And by the way, since r is square root of x squared plus y squared, that means r squared is x squared plus y squared. Therefore, e to the negative x squared minus y squared can be written as e to the negative r squared. So that's what I'm going to write here, e to the negative r squared times r dr d theta, where r goes from 0 to infinity and theta goes from 0 to 2 pi. Okay. Now, something magical happens. I was quite amused when I saw this for the first time. Hopefully you've learned that this cannot be integrated with whatever method you use. Whether you use integration by parts or U substitution, nothing works. But look, how about this one? You can do it, right? How? See, if you say this is u, right? Then what's that? That's like if you put
du is
negative 2r, right? Okay. So the way we can do this is by saying that this is from 0 to 2 pi of integral from 0 to infinity of negative 1/2. So e to the negative r squared times negative 2r dr. Okay. And then d theta. Okay. And I like this because if I set this as u, then du would be this much, right? If you differentiate negative r squared, this is du. So the integral of this thing inside will simply be negative 1/2 e to the negative r squared. Okay? And if you're not sure what happened from here to there, it's just plain U substitution, or you can just take the derivative of this using the chain rule, right? If you take the derivative of this using the chain rule, you have to pull out the negative r squared. Differentiating that gives you negative 2r, which cancels with negative 1/2, creating exactly r times e to the negative r squared. Right? Is that good? Right. Now, when you plug in infinity, what do you get? What's e to the negative infinity?
0.
0. E to the negative infinity is 1 over e to the infinity, which is 0. Okay, when you plug in 0, what do you get?
1.
1, but there's a negative 1/2 in front. So what you get is, you get square root of integral from 0 to 2 pi of 0 minus negative 1/2. Okay? So that's just 1/2. If you integrate 1/2, you get 1/2 theta, and you plug in 2 pi and 0 in there, what do you get as the integral of this?
Pi.
Just pi, right? Yeah, because this gives you 2 pi, but then 1/2 is multiplied, so you get square root of pi. Okay? So that's a cute result, that the integral of this Gaussian integral, e to the negative x squared, is a very hard one to do, but if you convert it to polar coordinates, suddenly you get square root of pi as your answer. Okay, so let's accept that as our first result. Okay, now tell me what the integral from 0 to infinity would be then.
Half it. 1/2.
Because this is an even function, right? I mean, I drew the graph for you, but it's an even function. So if you just integrate from 0 to infinity, that's just the half of the entire graph. So this will be square root of pi over 2. Okay, now what about integral from 0 to negative infinity of e to the negative x squared dx? Now that's a bit weird because usually you want to put the smaller number down, right? So we should switch these two around. What does that give us?
Negative pi over 2.
Yes, it will be negative, right? Because this will be, you need a minus sign to switch top and bottom. But then this much is the other half, the left side, which is again half of that because it's symmetric with respect to the y-axis. So this will be negative square root of pi over 2. So now I'm ready to define something called the error function, or just ERF. ERF of x, defined as you integrate from 0 to x of e to the negative t squared dt. Okay? Oh, no, I forgot. 2 over square root of pi. All right, so tell me what limit of x going to infinity of ERF of x would be.
1.
Yes, because I've just showed you that when x is infinity, this is radical pi over 2. So 2 over radical pi times radical pi over 2, they cancel each other, so you get 1. Okay. Limit x going to negative infinity of ERF of x would be? Negative 1 because of this. Right? If you plug in negative infinity to x, then this integral gives you negative radical pi over 2, but because of this normalization in front, it will give you negative 1. Right? Okay. Now, ERF of x prime is Oh, and this is such a nice question. This is actually something that could be in the final exam of Calculus 2. You're given this function and you're asked what's the derivative of this thing.
E to the negative t squared. No.
It can't be a function of t, it's a function of x, right?
Yeah.
Yes? No, it's not 0. Nice try. Usually 0 is an answer to a lot of questions. Oh, come on, nobody? All right. Maybe you don't recognize this, but suppose we want to differentiate such a function. Okay. So you have a function of t, you integrate, and then you integrate from 0 to x, and then you differentiate this by x. Okay. Well, let's call the antiderivative of small f as capital.
Is it e to the negative x squared negative 1? No, negative.
All right. I thought you were going to get it. No, we didn't. Okay. All right, so let's call the antiderivative as capital F. Then you would be plugging in x and 0, right? And you're differentiating this. So this would be capital F of x minus capital F of 0. And you differentiate this. Okay, what's capital F of x prime?
fx.
Fx, the small fx, right? What's capital F of 0 prime?
f0.
No.
No? Is it 0?
0. Because you plugged in first and then you differentiate. If you plug in first, that's a number. It's different than differentiate first and then plug in. Okay? Yeah, you plugged in 0 and then you're differentiating, so it's 0. Okay? So you get that. Okay? Does anyone know the name of this theorem? That if you take the function defined as an integral and you differentiate, you recover the function you started with. It has a name. You learned it in Calc 2. Okay. It's called the second fundamental theorem of calculus. Right? If something's named fundamental, it must be really important, right? Yeah. So it must have been the core thing that you learned in Calc 2. Yeah. Okay. All right, so therefore...
So it's just e to the negative x squared.
Yeah, with this one in front. Okay.
Yeah.
And simply put, all this is saying is that, oh, you integrated, but then you're differentiating again. What happens? Integration and differentiation should cancel. That's what it's saying. You integrate it, and then you differentiate. You integrate and then differentiate, you come back to the original function f. Now the only difference is that initially it was a function of t, but because you plug in x and you're differentiating by x, t now changed into x. That's what it is. That's called second fundamental theorem of calculus. All right, so what are we getting here? Well, these three facts, well, this fact says you get this as the derivative, and notice that this is always positive, right? Exponential functions are always positive, right? So what do we know about that, that function? The error function has derivative always positive. What does that mean? If the derivative is positive, we know that the function is increasing. Yes. So this will be a function that's increasing, always increasing, and it starts from -1 to +1. Okay? So the graph of the error function will be like this. Here's -1, here's 1, and it will be very close to -1 for a while, but then here it's going to go up, pass through 0. By the way, if you plug in 0, it'll be 0. That's another thing I forgot. If you plug in 0, you're integrating anything from 0 to 0. Of course, that'll be 0, right? So it'll be 0. And another thing is, because this function is an even function, if you integrate an even function, you get an odd function. If you integrate an odd function, well, not always true. If you integrate an odd function, it's always an even function, but if you integrate an odd function, then, and if the value at 0 is 0, then it's always, if you integrate an even function and the integration has the property that f of 0 is 0, then it's an odd function, okay? So we have an odd function that does this. Okay, so that's the graph of the error function. And this function, any function that behaves like a smooth transition between -1 to 1, so anything that's always increasing is smooth, meaning it's differentiable everywhere, infinitely many times. And then if it only has one inflection point, which is right here, such a curve is called a sigmoid. Now those of you who are trying to become data scientists might have heard this terminology in the realm of machine learning. Over there, they usually use 1 plus e to the negative x in the denominator. This one is the sigmoid. This one also has the graph that does that, but this one is steeper than the other one. Okay. Yeah. So they both look like that, so they're both called sigmoids. This is the preferred one used by machine learning people. All right. So that's the error function. And then there's also the complementary error function. Complementary error function, which is defined as ERFC of x is defined as 1 minus ERF of x. Yeah, so if you ever try to use Wolfram Alpha for your Calc 2 homework, I know you did, sometimes you would put some random stuff in there and it would spit out all kinds of strange things, and one of them, you may have seen ERF. Have you seen ERF spit out by Wolfram Alpha? You've seen it, okay, good, yeah. So if you ever wondered what that was, here it is, okay? Yeah. Now we're going to need these functions for solving the heat equation.